This tutorial presents a complete derivation of the Fourier transform for the function f of t equals sine t. We will develop the mathematical solution, interpret the frequency domain result, and examine the spectral characteristics of this fundamental waveform. Before we begin our derivation, let's review the essential definitions needed. The Fourier transform is defined as f of omega equals the integral from negative infinity to infinity of f of t times e to the negative j omega t dt. This complex exponential kernel allows to transform from the time domain to the frequency domain. The specific function in this tutorial is f of t equals sine of t, a pure sinusoid with frequency 1 radian per second. This Euler's formula representation of sine into exponentials will be crucial in this derivation, as it lets us work with exponentials instead of trigonometric functions. The Fourier transform of the sine function is initiated by the substitution of the trigonometric expression with its exponential equivalent. The integral from negative infinity to infinity of sine of t multiplied by e to the negative j omega t dt is considered. The sine function is then replaced by the expression e to the jt minus e to the negative jt, all divided by 2j. The constant factor of 1 over 2j is extracted from the integral. Within the integrand, two exponential terms are observed, e to the jt times e to the negative j omega t, and e to the negative jt times e to the negative j omega t, with the latter being subtracted. The exponents of the exponential terms are combined through algebraic manipulation, resulting in the expression 1 over 2j times the integral from negative infinity to infinity of the quantity e to the negative j times omega minus 1 t minus e to the negative j times omega plus 1 t dt. Subsequently, the linearity property of the integral operator is applied, allowing the integral of the difference to be expressed as the difference of two integrals. This yields the expression 1 over 2j times the quantity of the integral from negative infinity to infinity of e to the negative j times omega minus 1 t dt minus the integral from negative infinity to infinity of e to the negative j times omega plus 1 t dt. The delta function expressions are substituted into the Fourier transform equation, resulting in the following formulation: 1 over 2j times the quantity 2 pi delta of omega minus 1 minus 2 pi delta of omega plus 1. Algebraic simplification is then performed on the constant factors. The coefficient 2 pi divided by 2j yields pi over j, producing the intermediate expression pi over j times the quantity delta of omega minus 1 minus delta of omega plus 1. Through manipulation of the imaginary unit, noting that 1 over j is equal to negative j, the expression is further transformed. Multiplication by negative 1 within the parentheses yields the final formulation: j pi times the quantity delta of omega plus 1 minus delta of omega minus 1. The frequency domain result is interpreted as indicating that the sine function contains only two discrete frequency components. These components are located at omega equals plus 1 and omega equals minus 1 radian per second. The imaginary nature of the coefficients is associated with the phase characteristics of the sine function. Graphical visualization of the transform is provided. In the plot of the imaginary part versus frequency, two imaginary impulses are observed, one at omega equals minus 1 with value j pi, and one at omega equals plus 1 with value negative j pi. When the magnitude spectrum is considered, impulses of height pi are seen at both frequencies. This confirms that the sine function's energy is concentrated at exactly 2 points in the frequency domain. Several fundamental conclusions are derived from this analysis. First, it is confirmed that pure sinusoidal functions transform to Dirac delta functions in the frequency domain. Second, The sine function is found to possess frequency components exclusively at omega equals plus and minus 1 radian per second. Third, the imaginary nature of the coefficients is attributed to the sine function being an odd function in the time domain. Fourth, negative frequencies are understood as mathematical constructs representing rotational direction. Fifth, the amplitude factor of pi is noted to originate from Fourier transform normalization conventions. Finally, consistency is observed with the cosine transform result, which yields real, even delta function pairs. Several equivalent formulations of the Fourier transform result are commonly encountered in the literature. The generalized form for a sine function with arbitrary frequency is expressed as j pi times the quantity delta of omega plus omega naught minus delta of omega minus omega naught. An alternative convention utilizing a different normalization factor yields pi over j multiplied by the quantity delta of omega minus 1 minus delta of omega plus 1. When only the magnitude spectrum is considered, the expression pi times the sum of delta of omega minus 1 and delta of omega plus 1 is obtained. These variations arise from differing normalization conventions and representation preferences within the Fourier transform formalism. Verification of the result is accomplished through application of the inverse Fourier transform. The reconstruction integral is evaluated, yielding the original time domain function. Specifically, the integral of j pi times the quantity delta of omega plus 1 minus delta of omega minus 1 multiplied by e to the j omega t and integrated over all frequencies divided by 2 pi returns the sine function. This verification confirms the consistency of the forward and inverse transform operations.